Assalamualaikum warahmatullahi wabarakatuh, and a very good day to our lecturer. We are from Group 2, and today we are going to present about our project. The title for our project is a controller principle, which contain proportional P controller, integral I controller, derivative T controller, proportional integrity PI controller, proportional derivative PD controller. So a PID controller, also known as a proportional integral derivative controller, is a feedback-based control mechanism that is commonly used in a industrial control system and a variety of other applications that require constantly modulated control. A PID controller, which regulates a process, is made up of proportional P, integral I, and derivative D parameters. These criteria may be tweaked or changed to alter their impact on the process. In addition to these three parameters, it has a void and on-off navigation system. This controller is commonly used to control the temperature of residential heating and cooling system. This controller output is either at its maximum or minimum value depending on the direction of the fault.
Hello, hi, my name is ADILIAH binti ABDUL and my matrix number is CE210051. I want to explain about a methodology for this project. So, a closed-loop system such as a PID controller includes a feedback control mechanism. The system applies a feed points to access the feedback variable to create an error signal. This operation will be continued until the error is zero, at which time the value of the feedback variable will equal a fixed point. To get the desired outcome using a PID controller, there are a few options besides that. To address the mathematical model problem, we picked the using software option like MATLAB apps because it was easier to accomplish the required outcome. So we use a Ziegler-Nichols method. Nichols proposed that consistent and approximate tuning of any closed-loop PID control system could be achieved by a mathematical process that involves measuring the response of the system to a change in the set point and then performing a few simple calculations. This tuning method results in an overshoot response which is acceptable for many control systems and at least a good starting point for the others. If the desired response is to have less overshoot or no overshoot, some additional tuning will be required. The target amount of overshoot for the ZN method is to have the peak-to-peak amplitude of each cycle of overshoot be 1/4 of previous amplitude, as illustrated. The main advantage in using the ZN tuning method is that all three tuning constants, Kp, Td, and Ti, are pre-calculated and input to the system at the same time. It does require any trial and error to achieve initial tuning. This chief disadvantage in using ZN tuning is that in order to obtain the system characteristic data to make the calculation, the system must be operated in a closed loop, in oscillating condition, or open loop. We shall investigate both approaches. So this is a table for Ziegler-Nichols method. So this is a control type, which is a PID control. So we use P, PI, and the PID. So this is a Kp, Ki, and Kd. So we can see at the table. So that's all for me to explain about a methodology for this project. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad AZWAR bin OTHMAN. My matrix number is AA210032 from Group 2, Section 1. I will present how to simulate MATLAB for controller principle. So first, we need to design the opposite system for second order transfer function. We need a step block, a transfer function block, and scope block. Next, we need to find proportional gain, integral gain, and derivative gain by using this code. Value of K is 0.1, value for L equal to 0.025, value for T equal to 0.3 minus L, and next value of A is K L over T. T integral is T multiplied by L, and T derivative is L over 2. For our system, we use 1 over s squared plus 0.5s plus 1. Then we got the graph result and we compare with graph block response. Next, for P-controller closed-loop system, we need a step block, a P-controller block, a transfer function block, and we need some block to make feedback, and we need to change the sign to plus minus. Then we change the value proportional gain to 660 and we apply and we tune. And we can see the different block response and tune response, and we need to update the block and we get a new value for tuning corresponding to transfer function block. So next, for PID controller, same as block diagram before, we need transfer function block, a PID controller block, a scope block, a step block, and a sum block, and we change the sign to plus minus. Then we need to change the value proportional gain and integral gain to 792, and we change also derivative gain to 198, and we apply and we tune, and we can see the different block response and tune response, and we need to update the block and we get the new value for tuning corresponding to the transfer function block.
Okay, hi, my name is FADZILAH SYAFIQAH and my metric number is CE210206. And for the discussion, based on our observation, we could see that we manually turning the PID, PI and also P of the graph. And we will get the different answer from the auto turning for the closed loop system lah. And we also could see the percentage of the overshoot in controller, PID, PI and also parameters for the performance and robustness table as shown as I attach. If the rise time of the system is too long, the system may be operating at a suboptimal value for too long. And for PID, the value of overshoot and good settling time will, after we use auto turning, is the same for both block and the tune. And the answer, as you can see, for PID, the value of overshoot for the tune and the block is the same percentage, and the rise time is also the same, which is 0.708 seconds. And the closed loop is stable lah. And for the PI controller, the rise time is higher, which is 8.93 seconds for both tune and block. And for the overshoot, it will be decreased, which is 0.0189% for both value. And the closed loop is still stable. And for the P controller parameter performance and robustness, which is the time racing is 0.809 second for both tune and block, and overshoot is also the same, which is 58%, and the closed loop is stable, both is stable. Okay, so for the conclusion, lastly, for the open loop system, we also get nice result for the output from our equation for this system. And by using the auto-tuner, we can infer that the output waveform is significantly more stable than the one we had previously estimated lah. And in addition, we can create a lot more steady state response using MATLAB, auto-tuner, and lessens the distortion of our relative error, which is caused by a human mistake, which is calculating input. That's all.
To conclude, a model system is made by victimization the MATLAB simulating software packaging tool, adore the total PID controller, transfer perform, associate scope block. Besides that, the open loop system and closed loop system function successfully. Once an open loop system is applied to a motion system, there is no position feedback from the moving object. Though, if a closed loop control system is used, there is some sort of position into feedback to the motion controller and it helps within the positioning process. A fuzzy PID controller was applied to a stable, marginally stable, associated unstable second order system. So the results show that the fuzzy PID management outperformed the standard PID controller in achieving zero overshoot and make quicker transient response. This can be a current analysis and therefore the next part of the work can cover the ability to fine-tune the fuzzy gain automatically. Inclusion of prognostication and intelligent agent with the fuzzy algorithm will scale back the standardization time.